You're all very welcome. Thanks everyone for taking the time to come here today. So we're here to recognise two of our own researchers who've published in the last year. The aim of the award is to recognise the effort and frankly the achievement in having their work published. It's a great achievement, and really it's the currency that all researchers are judged by. So it's important that we try and recognise when it's done, and also try to encourage others to emanate them. So today we're going to give out two gold medal awards. For our best overall peer-reviewed publication, this award is going to go to Gabriel de Lima. And our second award is for the best first publication by one of our researchers, which is going to Zichao Tom. So this is judged by the acceptance date, and this is important because Tom had 2 manuscripts accepted within 1 week. So his first publication was judged to be one of the best. So both gold medal winners are exceptional researchers here. They've contributed greatly to the scientific field and to our own research community. So at this stage I'm just going to hand over to Kieran to hand over the awards, and I'll invite the two guys up.
Declan, get in. Hold on, get Declan in.
Perfect. And the second award is going to Zichao Tom.
You want to speak?
So both gentlemen are going to give a short presentation. I'll invite Gabriel up first because I see his paper on the desktop. So his paper is based on the accepted publication.
Ask later. Ask me later. Just speak out of that.
It's actually quite difficult to read the screen from here.
Yeah.
So Gabriel's publication, it's a publication in collaboration with the Institute of Ceramics and Glass in Madrid. It's based on bioactive composites fabricated by freeze-thawing method for bone regeneration applications. Gabriel, I'll hand over to you.
Right, thanks Declan, and thank you everyone for being here. So before I start, I just want to talk a little about me. So I don't know if everyone knows who I am. So I'm from Brazil. Okay, everyone is listening to me. It's real. So I'm from Brazil. The laser works. Yeah. So I'm in the state of Paraná, in the capital of Curitiba. All right. So you all think that Brazil is a little hot, right? But this is the picture from the last winter. So if you guys thinking going there, the south part of Brazil is really cold. So please bring your jacket, because another interesting fact is that in Brazil we don't have any heating system in our houses. So I had more cold in Brazil than here in the last 3 years. So just bear that in mind as well, okay? Right, so I'm from the Federal University of Paraná. So last year they completed 100 years. So they have a broad range of different scientific committees. So one of these that is where I studied was the physics and mechanical engineering. The laboratory where I studied was the laboratory of nanomechanical properties, and we have a partnership with a company called Neuorto, where they have implants of various parts of the human body, from the arms until the toes of the foot. And we have a partnership with them that we study the implants of titanium. So we try to improve the bioactivity of these titanium implants, because normally you can just insert the titanium in your body, because it's not going to communicate with the human bone cells. So one thing to do, we just use some coating here, and with this coating we try to improve the bioactivity. Normally it just improves a lot, and we test these nanomechanical properties but with nano indentation. This is one equipment that we use over there. So, right, so I decided to come here in EHE to study polymers. So then, thanks to Michael, he accepted my invitation, and then we start studying hydrogels. So hydrogels, they are 3D cross-linked polymeric networks, and they can swell on the water. So this swelling capability helps if you can have a drug or any active pharmaceutical ingredient to deliver a drug, and they can deliver in a very controlled manner. So this is helpful because if you release your drug too quickly, it can be toxic, and if you release your drug too slow, you won't have any effect at all. So you need to have a range here of how much of drug you need to release inside your body. So the hydrogels, the way we produce is securing. So the chains start to link with themselves, and with more cycles of freestyle, we have a more strong physical crossing, so we have more strong polymer. So another important aspect of hydrogels is that we can have a smart hydrogels. So smart hydrogels is they can be censored to things in the body that can react to. So for example, they can react to pH, to temperature, the polymers can react to that, and then for example they can swell more or they could swell less depending on the pH of the environment. So that's very good because you can target the delivery of the drug to any specific part of the human body. Right. So with this introduction that I said before, the objective that we did in this work here was to use a synthetic polymer and produce, and the only problem with the synthetic problem is that they are not very bioactive. So they can interact with the human body too well. They don't react with the human bone cells. So we add bioceramics. So the bioceramics helps to improve the bioactivity, and not only that, we decided to look further into a disease called osteomyelitis. So this is a drawing here that shows the disease. Normally is done because of the Staphylococcus aureus, because of an infection. And one way to stop these to proliferate in the human bone is to use a polymer to act as an anti-infection barrier. So that's what we try to do in this work, to produce a polymer, a hydrogel in this case, that can act as anti-infective barrier, but can also help to regenerate the bone using the bioceramics, right? So how do we do this? We use the alpha-tricalcium phosphate. This work was done with Ceramic and Glass Institute. They produced the ceramic with tricalcium phosphate, wollastonite, and talc. And they synthesized and compacted these ceramics to obtain two different porosity distribution, one we call monomodal and bimodal. These two porosity distributions we added inside our PVA that we used of 5% of PVA, and we also added 50% of polyphilic acid. So the PVA had a molecular weight of 4,500 and a hydrolysis of 98%, and the polyphilic acid had a molecular weight of 3,000. So the interesting fact here is that we did a lot of variations here in this work. So with the tricalcium phosphate, we did two different parameters using the monolayer and the bilayer, and we used two different concentrations for these two different ones. The two different porosity distributions, one with 5% and the other 25%. After that, we also used two different concentrations of 1 cycle of freestyle and 5 cycle of freestyle, just to understand how is the material or composites are going to interact. So if we look at the morphology of these samples, we can see that if we increase the concentrations of the ceramic, we have a more porous material. And the porous is an important factor if you're thinking about cells in the human body, because the cells needs to attach to a porous materials. If they are not very porous, the cells can attach, and the bioactivity or the regeneration of the bone won't occur. So Another interesting aspect is that as you increase the freestalling, the samples start, the ceramics, the composites start to become more stronger. So as you can see here, the walls starting to compress themselves, and as you increase, with 5 cycles of freestyle, the walls are more detailed here. Right? But we didn't see any difference with monomodal ceramic and bimodal ceramic. Right, so we got some good results with the SEM, and we investigated now the microstructure. So the microstructure was interesting because we saw 3 important aspects here. The first one was that this is a ceramic alone. So you can see the peaks of the ceramic starts to 1,100 until 600 here. And when we add the ceramic into the polyvinyl alcohol, the polymer that we are using, we see the ceramics incorporated. Not too detailed here, but it seems to be more detailed and increases its peaks on the bimodal ceramic. So we didn't see any difference between monomodal and bimodal on the morphology, but we actually did see on the microstructure. Also, we observed that this peak here corresponds to the crystallinity of the PVA. So the crystallinity is a good aspect to know how much strong is your polymer. So in this case here, with the bimodal and 5 cycles of freestyle, we have a very strong and detailed peak of the crystallinity of the PVA. And we also notice after adding the ceramics, a new peak here. That's the group due to the PVA, polyacrylic acid, but it doesn't appear on the other peaks, only on the ceramics, after we add the ceramics. Right, so we detected we observed a difference after we added the ceramics. We also noticed that it increased the crystallinity, and it was incorporated by the FTR. And we now look at the swelling. So the swelling, with 1 cycle of freestyle, the samples swell to a maximum until 3 hours, so they swell very quickly and reach the equilibrium after 3 hours. And then with 5 cycle of freestyle, they only reach the equilibrium after 30 hours. So it shows how much stronger the samples are. And here it also shows how the sample, even after 30 hours, still didn't actually degrade themselves. Normally, if you actually add these sensor capabilities to these hydrogels, the sample doesn't start to degrade. They are not very strong. So the samples that we produce here, they are very defined and very strong. So it's able to be used. Right. So after all these results, we decided to investigate the mechanical properties. So with the rheology results showed here, that after we added the ceramics, a very strong peak here that show how much stronger the material are after 5 cycles of freestyle, and at the 25%. So the 5% didn't actually have a difference between the normal materials compared with the ceramic, well, with the addition of the ceramic, but with the addition of ceramic with a highest concentration, 25%, have a very strong mechanical property here. Both the monomodal porosity distribution and the bimodal porosity distribution. So after that, we also look at the DSC. The DSC also showed for us that a good mechanical property, a good distribution, and a thermal response. Because if you see here, these are the materials alone: the ceramic, the polyacrylic acid, the PVA, and here is a PVA with polyacrylic acid. When we add the ceramics with 1 cycle, the materials they look similar to the polyvinyl alcohol and polyacrylic acid, but as we increase the cycles to 5 cycles, we see a normal pattern similar to the PVA, like this one. So this shows how much improved the material are now. Right. So after all of these, we then decided to investigate if we can add we added the cyprofloxacin on these polymers to actually see if they can combat the Staphylococcus aureus bacteria to inhibit the proliferation in case we are using them as an anti-infection barrier. So as you can see here, both the monomodal and the bimodal was very effective. and we got a zone of inhibition disk, and we also noticed that there a significant difference between the mono model and the beam model. So the mono model in this case was better than the beam model here. So in conclusion, we can see that the materials was very porous, and the ceramics particles was embedded between the material, the polymer, and it had a very excellent improvement of swelling and mechanical properties, as you can see here. So why is this important? Is because normally, if you have a very increasing swelling, normally you have a low degree of mechanical properties. So if your swelling increases compared to your material without the ceramic, what it tends to occur is that the ceramics would decrease the mechanical properties, but this effect shows the contrary. So now, before I just go to the acknowledgements, I just want to give here a little tips for the people here who are starting to write. I hope because if I knew this before, it would help me a lot. So the first tip is like, don't give up if you got rejected in the first, second, and third attempt to submit your paper, because you never know what the editor was thinking when you're trying to submit your paper. So don't think your work is bad or worse. The second one is, you have doubts as to where you should submit your paper, try the ones you see the most. So this is highly affect the relevance and help to target your audience. So if you see that a lot of that journal, of specific journals, you try to go to that route, because it will help the authors, because they are normally reading that journal, and you help target the audience. And finally, if you think that your first paper is not good enough for a publication, but other things otherwise, know that you get the hang of it, and you improve the next paper to a style that you like as you write more. But this is only happy if you give your first step, right? So I just want to thank you now, my funding agent, Science Without Borders, the Captain's Foundation, and my supervisor, Michael Nugent, Declan, and all the people and staff from AIT and the Ceramic and Glass Institute. And all of you, thank you very much.
About turf ash composites. This was done in conjunction with calcium carbonate composites. He's done a lot of work, obviously. It was done in conjunction with industrial partner, Morgan International. It's led to 2 publications so far, and hopefully 2 to 3 more, which are under review and in progress. So Tom, do you want to come on up and give your story? Thanks.
Yeah, before we go through the paper, we just like to talk about the journey of my publications. This is my 3rd year college. That's placement in Germany, and that's the first time I got my name on piece of paper, right, or on the paper. And finally I started my research, and that was January 2012 I started. And 3 months after, we got one paper finished, and win the best Irish paper in 3rd Malaysian Ireland Journal Symposium. And that's I got my PhD lab in 2016, and so far we have 6 paper completed, and 3 paper published, 3 paper under reviews, and say it's good, you know. And this part of the paper, the writing is helping research. Okay, our research is moving from research to reality. And the actual bonus is because I'm writing, my daughter is also writing. Her book is The Magic Potion, and she also won this one, write-a-book competition. And let's talk about, it's all goodness, you know, when you're writing, a lot of things come out, this not expected. And let's talk about this paper. This paper is my first journal publications. It's not my best paper, but I remember the whole process. We did this test, and we created this concept. Calcium carbonate is one of the most commonly used filler for plastic industry. And we find it's cost-effective, water-resistant. But the novelty of this research work is we have innovated a new way and effective way to surface treated calcium carbonate pellets. And our new method can significantly reduce the void content of the composite but increase the mechanical property, also increase the density. Instead of putting sandbags and addition weight parts, you can put in calcium carbonate to increase the weight, strength, but also cut the price. This paper was published in Applied Surface Science in 2016. The whole lab work of this job was completed 2012. Yes, I used 4 years to publish paper. It's a very long time. And the whole process was I can remember the whole process. That's part of that. I finally started writing. I was trying to avoid that writing all 2 years. Because I said it's hard, because it's most commonly used filler, so hard to find selling points of contributions. So I finally started writing in 2014, and that's how many of the version I have for that paper. The whole paper was rewritten completely 2 times. I finally got published. And the second paper was published 2 weeks after this paper. And so because it's long, because I was tortured, I was failed, so I learned a lot from this writing, from this paper writing basically. And today I like to share 3 of my thought of what I learned from this writing. I think the most important. The first, do not wait. Okay? Now in front of the camera, in front of all the people here, I promise I'm going to start writing today. Again. Seriously, because I see maybe everybody should start thinking about your paper now and start writing today. I wait for 2 years. Nobody will write for me. At the end, I have to struggle on 12 different versions until I find the paper finished. You know, the earlier you write, the better. I say, you know, because otherwise I have to run through the lab and go back to testing all these things. You know, so it was hard. The second thing is you have to find a strong and clear selling point. They call it contributions. Very strong selling points. For this paper, the selling point is the new way to surface treated calcium carbonate. You know, so that was difficult because this calcium carbonate is so common used. It's like I feel like I was in the really old gold mines to try to find a small piece of gold. So difficult. So that's why it took a long time. So find strong selling points. And the last tips is this big man who catches a very small fish, but he was so happy about it. He loved it so much. So the last tips, I would say, be confident about your work. Okay, and you got all the positive energies about your work, confident, love it, and once you create a small piece of word on the piece of paper, and the energy will transfer on that paper, and they will convince people to get published. I say. So I say the whole meeting is about try to let people to write. So this is my contributions. Thank you very much.
Thank you very much, Tom. Just a few small things left. The award will run again this year. So the award is based on the MRI, unfortunately for people not in the MRI. So this year it was the first author whose first affiliation was the Materials Research Institute. Hopefully we can expand that out in future years. This year we're going to move it that no matter where you are in the author list you can apply, but it'll obviously be weighted towards the first author because it's the first author who's actually going to write the publication. Silver medal awards went to Yan Yan Chen and Elaine Kenny. Yan Yan Chen for halloysite nanotube reinforced polylactic acid composites. Unfortunately, she can't be here today, and neither can Elaine, as she's working in industry. In this case, Elaine published work on melt extruded bioresorbable polymer composites for potential regenerative medicine applications. So a lot of the work that Elaine has done has been put into a book that we're writing at the moment on bioresorbable polymers. So a point I like to make to researchers is, like I said before, the currency for research is your publications. You're all sitting around this table because you chose to be researchers. By that definition, you have chose to write publications. This award ceremony is to try and recognise people who have gone to that effort. Both guys did pretty much say it's not easy. It's hard work, but in the end of the day, you all need to get a thesis. Your thesis has to be peer reviewed. If you have a peer reviewed publication to go with your thesis, it strengthens it. You need to write a thesis. You need to write a publication. I'm sure the guys will probably say that the publication helped them write their thesis. I know mine certainly did. Start writing something. If you don't know fully what to write down bullet points. Just start. A start is a good place. You know, even the journey of 1,000 miles will start with one step. You need to write down something, build on it, and eventually you will get 2 years later, hopefully sooner, some publications. Now, thank you very much for your attention. I think we're going to just stop the video there, and we can take some questions for the two guys.